In the second approach, let's try to use disjoint set union. So our first task is to determine which indices belong to the same connected component, right? So in this approach, we try to use union find data structure to accomplish this. So first, we will union all of the vertices that share an edge. So if AB, OBA exist in pairs, that means the vertices AB share an edge. So after which, all of the vertices with the same root will belong to the same component. So in this way, we just by looking at the root node for each vertex, we can put the vertices and the characters of these indices in the separate list, which with the corresponding to the component that belongs to, right? So then, similar to the previous approach, we will sort the list of characters that belong to the same component and place the ith character and the ith index in the string, smallest string. And we should note that we don't need to sort the list of indices in this approach, because as we iterate over the vertices in ascending order, we will also sort the vertices that belong to the same component in ascending order. So let's try to create UF, which is an instance of the union find class. It is being initialized with a parameter length of s. So this is creating an empty union find object with length of s number of vertices. So each vertex is representative of itself with rank of 1. So this is done by keeping track of the connected components in the graph, which is represented by the input string s and the list of pairs. So now, let's go back to the beginning and create a union find class. It will be used later on try to find the root of each vertex and try to form a connected component in the graph. Let's try to create an instance of union find class. The size of the parameter passed to the constructor, which determines the size of the list and the number of vertices in the union find data structure. And then let's try to initialize two lists, root and rank. The root list contains the indices of each vertex, which represent the root of each vertex, with the vertex initially being its own root. And the rank list contains the rank of each vertex, with each vertex initially having a rank of 1. So first, we iterate over the pairs. For each pairs AB, we try to perform the union operation for the vertices A and B. So this union operation will update the root of each vertex to point to the same root. So it effectively merges into two vertices into the same connected components. And because the union operation takes O of log of V time, so we iterate over E pairs. So the total time complexity of this step is O of E log V time. The time complexity here is O of E log V. Well, the E is the number of edges in the pair of lists, and the V is the number of vertices in this graph. And this is because for each edge in the pairs list, we are performing the union operation on the vertices at the endpoints of that edge. So the union operation in this implementation uses the path compression and the union by rank technique, which have an average time complexity, which is O of log V. So for each operation, therefore the overall time complexity for this loop is O of E log V. We try to iterating over a list of edges, which is represented as pairs. So for each edge, we have two vertices. We just extracting the source vertex represented by the first element of the pairs, and we extracting the destination vertex, which is represented by the second element of the pairs. So this is done. And then we can perform the union operation on the union find data structure. Well, it merges the set containing the source vertex with the set containing the destination vertex, which make the source and the destination part of the same connected component. So we create a dictionary, rootToComponent, in Python. So that maps a root vertex to a list of vertices that are in the same connected component as our root vertex. So the key of the dictionary is the root vertex, and the value of the dictionary is a list of vertices that are in the same connected component as our root vertex. So this data structure is used to group all of the vertices that are in the same connected components together, so that it can be sorted and processed together. We try to iterate over all of the vertices of the input string S. So for each vertex, we try to find its root by using the find method from the union find class. We're just checking if the current root of the vertex is not already present in the rootToComponent dictionary. So if it is not present, then we just initialize an empty list for that root in the dictionary. So for that root in the dictionary, which we are used to store all of the vertices that belong to the particular component. So this is used to group the vertices that are in the same components by the root. And then it groups the vertices that have the same root in dictionary, which is called rootToComponents. So the key of the dictionary is the root of components, and the value is a list of vertices that belong to that component. So in this way, we can easily access all of the vertices that are in the same connected components. The time complex here is O of V because we iterate over each vertex in the string. So for each vertex, we perform the find operation on the union find data structure, which takes O of alpha of V time. Well, the alpha of V is the inverse Ackermann function. This function is extremely slow, so it is considered to be constant for the most practical value of V. So we can say that the find operation takes O of 1 time, so therefore the overall time complexity of this loop is O of V multiplied by O of 1, which is also O of V time. And the space complexity here is O of V, as we just create a dictionary with V keys. So let's try to create an empty dictionary called rootToComponent, and then we try to iterate over the vertices, which is the indices in the input string S. So for each vertex, we perform a find operation on the UF object, which is an instance of the union find class, to get the root of the vertex. And then we try to check if the root is already present in the dictionary. If it's not, we try to create a new key value pairs in the dictionary, where the key is the root and the value is an empty list. So finally, let's try to append the vertex to the list, which corresponding to the root in the dictionary. So this process will groups all of the vertices that are in the same component under the same root, which they have the same key in the dictionary. The time complex here is O of V log V. This because for each component, we iterating over the indices in the component, which is V operations, and then we sorting the characters in the group, which is log V operations. And since we are iterating over all of the components, so the total time complexity is V log V. So regarding the space complexity, it is O of V, as we storing all of the characters in the group in the characters list. So for each vertex in the graph, we are creating an empty list characters, since the number of vertices is equal to the length of the input string S. So the size of each list is dependent on the number of vertices, so the space complexity is O of V. The time complexity here is O of V. Well, V is the number of elements in the list indices. This is because we are iterating over the list indices once and performing a constant time operation of adding the character at each index to the list characters. The time complexity of this loop is O of V. Well, V is the number of the characters in the input string S. This is because the loop is iterating through the list indices and the characters list, so it's performing a constant time assignment operation for each iteration. And the space complexity of this loop is only of 1 because it only performing assignment and it is already existing list small string and not creating any new data structure. We try to create an empty list called smaller string, which is the same length as the input string S, and then we try to iterate over the values from the rootToComponent dictionary. Well, each value is a list of indices, so for each of these lists, we try to create a new list called characters, and then we just append the corresponding character from the input string S to the list by using the indices. And then we try to sort the characters list alphabetically, and then we're using the enumerate function to iterate over the characters list, which assigns an index to each element of the list. So for each characters, we assign the characters to the corresponding index in the smallest string list, and finally, it joins the smallest string list into a single string and returns it.